I'll be giving you just a very brief, high-level overview of what the pipeline looks like in terms of spectroscopic data. And we'll be going into more details in what individual steps and pipelines are doing to the data in the following notebooks. So this is just to kind of give you an overview and sort of a graphical representation of all the things that are going on. It's quite complicated. Before we get to that, just so that everyone's sort of on the same page, and to put everything into context, I just wanted to do a quick overview of all of the many spectroscopic modes that JWST has to offer. For convenience's sake, I've grouped these into three sort of categories that roughly depend on how the pipeline treats the data. So the first one is the simplest modes are those looking at single targets, either by use of slit spectroscopy or slitless in some cases. This includes time series observation geared modes such as NIRCam GRISM time series. Also NIRIS has a similar single object slitless spectroscopy. Those two modes together are complementary and spanning the full near-infrared wavelength range of roughly 1 to 5 microns. NIRSpec has a fixed slit spectroscopy mode using one of 5 fixed slits of varying widths and lengths to observe single targets using the full wavelength range available for that instrument. And then specifically one of those slits, the 1.6 arc second square aperture, is used for a bright object transit spectroscopy or BOTS mode. Again, same wavelength coverage, but in that case geared towards time series observations such as exoplanet transits. And then finally, in the mid-infrared, MIRI has the low resolution spectroscopy mode, or LRS, available in either slit or slitless versions, covering a mid-infrared wavelength range of 5 to 12 microns. And so again, all of these modes are really optimized for single targets, many of them for time series observations. They have a lot of similarities in processing, although there are somewhat different methodologies depending on whether a slit is used or whether it's a slitless GRISM observation. In all cases, the pipeline will produce a single combined data product in the end, which is either a combination of multi-exposures, or in the case of time series observations, it will be a set of integrations packaged together in a single product. Just to show you a few examples of what some of these data look like at the top, shows you an example of NIRCam GRISM TSO observation. In the middle is NIRIS SOS. And then down below is NIRSpec fixed slits. The top two are simulations, and the bottom is a ground-based internal lamp exposure showing all of the 5 slits and how they're imaged onto the detectors. Next category is multi-object spectroscopy. There are three main modes for this. NIRCam and NIRIS both offer a wide-field slitless spectroscopic mode using GRISMs, and again, as in the single object case, these are complementary in wavelength coverage. And then NIRSpec has a multi-object spectroscopic mode, or MOS, that's enabled using the microshutter array, which allows configurable slitlets to be opened on multiple sources in the field. Now, of course, owing to the more complex nature of this kind of data, requires more complex algorithms in the pipeline than in the single object case, and in particular, a lot more work in managing metadata, such as source positions that need to be tracked as the pipeline does its processing. And the final combined data products in this case are organized by source. So basically one set of final data products per source where all exposures get combined together. And then here's a few examples of what these data look like. On the left shows sort of a movie showing the full set of data that you would receive for the nearest wide field slitless mode, where the grisms are rotated by 90 degrees to enable disentangling of overlapping spectra. And then on the right shows an example of actual data from the ground using internal lamps, where small slitlets have been opened with using multiple shutters in each slitlet. You can see how the light is dispersed onto the detectors, and also showing how the fixed slits are always open to sky and are also available simultaneously. Finally, the last category is integral field spectroscopy. There's two modes for this. The NIRSpec, integral field unit spectroscopy, or IFU, and then MIRI, medium resolution spectroscopy, or MRS. These provide spatially resolved spectroscopy for NIRSpec, covering the full near-infrared wavelength range, and then MRS, the full mid-infrared wavelength range of 5 to 29 microns in that case. And here the data products provided by the pipeline are rectified 3D cubes in RA, DEC, and wavelength space. And then this slide here just shows you some examples of what this data looks like, actual data and schematically. At the top right shows you a schematic of the optics for the NIRSpec IFU and how the image of the sky is split up into slices using an image slicer, and the spectrum for each of those slices is re-imaged onto the detector, as demonstrated in the top left. This is again, this is actual data from the ground using internal lamp exposures, showing you how the spectrum for each of the slices is imaged at sort of the top and bottom of each detector. And again, the fixed slits are always open in the middle of the detectors. And then below, once the pipeline finishes its processing, it produces a spectral cube shown schematically like this, where you get both spatial and spectral information. And just a really quick now overview of what the pipeline's doing. Joe already did a description of what happens at stage 1, which produces as a data product a count rate image per integration, or averaged over multiple integrations. That goes as input into stage 2, which for spectroscopic data will calibrate the world coordinate system, such as spatial and wavelength coordinates per pixel, and corrects for a variety of different instrument effects, throughput, flat field, etc. And the final data product from that stage, the main data product, is an exposure level calibrated 2D unrectified spectrum, as well as quick look products that are rectified 2D and 1D extracted spectra. The calibrated 2D spectra produced by that stage goes as input into stage 3, which then takes multiple exposures and combines those together into one final combined product, the primary products being rectified 2D spectra and 1D extracted spectra. And then for the TSO modes, this will be calibrated integrations. For more details on the data products at each of these stages and how they're structured and what information they contain, I refer you to the first JWebbinar series. Again, Joe already went through stage 1, so I won't belabor that here. Here is stage 2, and you can see it's quite complicated. There's a large set of steps. Which steps get applied to which data depends greatly on both mode and instrument. And here are sort of, I've grouped things by these basic categories of observation that we already went into. I'm not going to go into any detail on individual steps. The following notebooks, we will demonstrate for you each of these steps and talk about what they are doing to the data in a little bit more detail. I just leave this here for reference. Stage 3, for non-TSO spectroscopy, again, it's a little bit simpler, but still the steps that are applied depend again on mode and instrument. This includes primarily things like the alternative method of background subtraction, master background, an additional outlier detection step, and then final combination of data into a final regularized grid, either a 2D grid for the 2D spectral modes or 3D cubes for the IFU modes. And then finally, stage 3 for TSO spectroscopy, since we aren't combining exposures in this case, it's much simpler. There's basically just 3 steps, including an outlier detection, comparing a stack, the full stack per pixel, and identifying outliers from that, and then finally extracting a 1D spectrum for each integration, and also calculating white light photometry from that.